In this video, we're going to take a look at some additional examples of evaluating indefinite integrals using integration by parts. As a reminder, the integration by parts formula says that the integral of u dv is equal to u times v minus the integral of v du. The idea here is that we can rewrite the integral on the left-hand side in terms of the integral on the right-hand side, which will often be simpler and more easily evaluated. Integration by parts can be combined with other integration techniques such as substitution, as we'll see in our first example. In this example, we want to evaluate the integral of x cubed e to the x squared dx. If we try to use integration by parts alone on this example, we run into a bit of a problem based on the function e to the x squared. This is a function whose antiderivative is unknown, and so e to the x squared cannot possibly be dv, which means it would have to equal u. And then when we use du, we end up having to use the chain rule, and we get a very complicated expression. So integration by parts alone will really not lead to any kind of useful approach to this problem. Now you might notice that this integral looks somewhat like a substitution integral as well. We have a composition of functions e to the x squared, and the inside function x squared has a derivative of 2x, and we do have a factor of x being multiplied here. The problem with substitution is that we actually have too many x's. We have x cubed instead of just x. However, if we cleverly rewrite our integrand as x squared times x e to the x squared dx, then we see that we're set up perfectly for a substitution in the second part of our integrand. We have x e to the x squared, and we just have to deal with the x squared that we're multiplying that function by. So we can go forward and try a standard substitution approach to this integral, even though it doesn't exactly line up with what we would normally expect for a substitution example. We can start by letting w be the inside function x squared. And notice here I'm using w instead of u in order to reserve u for use when we do integration by parts in the second step of this example. However, once I pick w to be x squared, we know the derivative of w is going to be 2x dx. And in our integral, we do not have a constant 2. We just have x dx. So I can divide both sides of this by 2 and get dw over 2 is equal to x dx. At this point, I can substitute everything into our integral. And notice we have, in this case, the integral of x squared, which we know is w. Even though that wasn't the x squared we used for our substitution, it is equivalent to w, so we can replace it with w. And then the rest of it is our standard substitution. We have e to the x squared, which is e to the w, and we have x dx, which is dw over 2. And so with a little bit of cleaning up, we see that we have the integral, or 1/2 of the integral, w times e to the w dw. And now looking at this integral, we see that this is a very standard integration by parts example. And so we can apply integration by parts to this new integral in terms of w. So in order to do that, we can let u equal w, dv equaling EW dW. And this means that du is going to equal dw, and v will equal e to the w. We can substitute all of this in to the integration by parts formula, and we're going to get 1/2 times the expression uv, which is w e to the w, minus the integral of v du, which is e to the w dw. And of course, this integral is quite easily computed. This is just going to be e to the w. And of course, we want to make sure we have a plus c, our arbitrary constant of integration, tacked on there at the end. And the last step that we need to remember is that we also did a substitution at the beginning up here in blue, and so we do need to go back to our original variable x. And so we can replace w with x squared everywhere that it appears. So our final function here will be 1/2 times the quantity of x squared e to the x squared minus e to the x squared all plus c. And so in order to get this, we first had to make a substitution of w equals x squared, and then use integration by parts on the resulting integral in order to end up with our final solution. If you'd like to try a similar example, you can pause the video and evaluate the integral of x cubed sine of x squared dx. The full solution will appear in a few moments. This integral is evaluated very similarly to the previous one. We start by making a substitution with w equaling x squared and dw over 2 equaling x dx, and that gives us the integral of 1/2 w sine of w dw, and of course we can pull the 1/2 outside, and so we just need to evaluate the integral of w sine w. In order to do this, we can use integration by parts. We can let u equal w and dv equals sine w dw. From that, we get du equals dw and v equals negative cosine w. And substituting everything into the integration by parts formula gives us 1/2 times the quantity negative w cosine w plus the integral of cosine w dw. The integral of cosine w is, of course, positive sine w. And then at last, we go back to the variable x by replacing w with x squared throughout the expression, and this gives us a final function of 1/2 times the quantity negative x squared cosine x squared plus sine of x squared all plus c. Notice that those parentheses around the two trig terms are important because we need to multiply both of them by 1/2 since 1/2 was factored outside of the integral in the first step of our problem. In this example, we'd like to evaluate the integral of e to the x sine x dx. At first, this seems like a very straightforward integration by parts problem, since we have a product of two functions that are easily differentiated and anti-differentiated, but as we'll soon see, there is sort of a problem that comes about when we try to compute this integral using integration by parts. Our first step is to pick u and dv for our particular integrand, and here we have e to the x and sine x, both of which are easily differentiated and easily anti-differentiated. And so we'll go ahead and just pick u to be e to the x and dv to be sine of x dx. And of course, that means that du will be our derivative of e to the x, which will just be e to the x dx, and v will be the antiderivative of sine of x, which is negative cosine of x. Once we pick all of these values, we know from the integration by parts formula that the integral of e to the x sine x will be u times v, which will be negative e to the x cosine v, minus the integral of v du, and v du will be a negative, so we'll bring that outside the integral to make a positive integral of e to the x cosine x. And so we've used integration by parts to rewrite our integral in terms of the integral of e to the x cosine x dx. Now, this integral is not one that we can easily evaluate. In fact, it's actually very similar to the integral that we started with. The only difference is that now we're multiplying e to the x by cosine of x instead of sine x. And so at this point, we might think to try this one more time since we did not get an integral that's more complicated. We got a very similar difficulty level integral here. And so we're going to try applying integration by parts to this second integral, just like we did for the first. And so like in the first example, we're going to let u be e to the x. We're going to let dv be the trig function. In this case, that would be cosine x dx. Then du will be e to the x dx, the derivative of e to the x. And v will be the antiderivative of cosine x, which is sine of x. And so we get that the integral of e to the x cosine of x now will be u times v, which will be e to the x sine x, minus the integral of v du, which will be e to the x sine x dx. At this point, we should stop and take a look at what we've done. We've applied integration by parts twice to our original integral, and we have not yet produced a simpler integral. In fact, if you look at the integral that we ended up with after the 2 steps of integration by parts, you'll notice hopefully that it's exactly the same as the integral that we started with at the beginning of the example. So these 2 steps of integration by parts just cycled us through right back to the original integral. At first glance, this seems to be incredibly unuseful. However, given that we now are back to the same integral, we can actually use some clever algebra to solve for that integral. To see how we do this, we start with the initial equation that we found by applying integration by parts to the original integral the first time. That is that the integral of e to the x sine x dx is equal to negative e to the x cosine x plus the integral of e to the x cosine x dx, and then replacing the integral of e to the x cosine x dx with the expression that we found in the second step of integration by parts, namely e to the x sine x minus the integral of e to the x sine x dx. When we do that, we get that the integral of e to the x sine x dx is going to equal negative e to the x cosine x plus e to the x sine x minus the integral of e to the x sine x dx. We can now add the integral of e to the x sine x dx to both sides of this equation. This is valid since the integral is just a collection of antiderivatives and therefore just a function plus an arbitrary constant c, which we can adjust on both sides. And so we can add this term to both sides, and on the left-hand side, we see that we're going to end up with 2 times that integral plus itself. So we have 2 integral e to the x sine x dx. And on the right-hand side, the integrals will actually cancel out, and so we're just left with negative e to the x cosine x plus e to the x sine x. Now we want to find the integral of e to the x sine x dx without the 2 in front, and so we can simply divide both sides by 2 or multiply by 1/2. And in doing so, we find that the integral of e to the x sine x dx will simply equal 1/2 negative e to the x cosine x plus e to the x sine x. And of course, we have to remember to add our arbitrary constant plus c here at the very end, since we do have an indefinite integral. And so our indefinite integral here is 1/2 times the quantity negative e to the x cosine x plus e to the x sine x, all plus c.